Hello, welcome to Forest Learn. This video is an introduction to stationary waves. Previously we've discussed the principle of superposition, which explains what happens when two waves or wave pulses meet. The principle of superposition will also explain what happens when two progressive waves shaped like a cosine or a sine graph meet as well. But the question is, what will the outcome look like? We can easily generate this situation using a simulation. But before we do this, let's take a look at what happens when a wave pulse propagates towards a fixed end. So here I'm gonna generate a wave pulse in a moment, and it's gonna travel to the right and reach this end here, which is fixed. You can see this clamp here, and so this green particle or bead here will not move. So let's take a look at what happens. There are a couple of things to note here. When the pulse reflects to the left, notice how it got inverted. So the pulse, when it was moving to the right, it was initially a crest, shaped like a crest, and now it's shaped like a trough. Notice also that the depth of the trough, or the maximum displacement, is the same, or has the same magnitude as the height of the crest. And throughout this video, we'll be assuming that when waves reflect, the reflected waves have the same maximum displacement or amplitude as the incoming or incident waves. Be aware though that there can be scenarios where this is not true. For example, when ultrasound waves reflect off a wall, the reflected waves have a smaller amplitude due to some of the ultrasound being absorbed by the wall. We can also examine the reflection of progressive waves shaped like a sine or a cosine. Notice that the amplitude of the reflected wave is identical to that of the incident wave that traveled to the right, which is precisely what I mentioned a moment or two ago. It's also worth noting that the frequencies and wavelengths of the incident and reflected waves are the same as well. Now, let's see what happens when incident waves are generated continuously and travel to the right to be reflected. Before I press play, I'll just point out that this end that will vibrate up and down is often referred to as a vibration transducer, and the waves that will be generated will have a frequency of 1 Hertz and an amplitude of 0.25 centimeters. So let's take a look at what happens. We can see that nothing particularly interesting is happening. What you're seeing is really just the outcome or the result of superposition between the incident waves that move to the right and the reflected waves which travel to the left. Let's change the frequency to say 1.5 Hertz and see how the picture looks then. Once again, you can see that the picture remains pretty unremarkable. Now, let me make some tweaks to some of these variables here. Let me bump down the amplitude. And let me change the frequency to 1.26 Hertz. Let's see what goes on now. Notice that there is a distinct pattern to what we are seeing now. In particular, let me point out that there are certain points or particles. So for example, this green particle here, and then this green particle here, which are effectively motionless or stationary. In contrast, the green particle in between these two green particles, so this one here, is oscillating with a large amplitude. So what we're looking at here is an example of a stationary wave. And let's discuss the features of a stationary wave further. So I mentioned a moment ago that in a stationary wave there are certain particles or points on the wave that appear to be motionless or completely still. And that's these four green particles here, 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 and here that I've labeled with a capital N. And the capital N stands for node. Alright, so this is a common abbreviation. So points that are motionless on a stationary wave are known as nodes. You should compare the existence of these nodes to a progressive wave. If we were looking at a single progressive wave, say traveling to the right, all the particles would be oscillating. Right? There wouldn't be any particles that would be completely at rest at all times. So this is a key difference between a stationary and a progressive wave. The fact that we have a node at the right end over here, that's not surprising, because remember, this is a clamp, so this green particle, it's clamped, okay, so it can't move. So that's not surprising. Over at the left end over here, where this vibration transducer moves up and down, you might have noticed from the simulation that actually the amplitude of this transducer is relatively small. So this node, this green particle here, even though it's moving up and down, because it's moving with such a small amplitude, it effectively qualifies as a node. Right, so we regard this end as being effectively stationary. The big surprise is the fact that we have this green particle here and over here being completely still. Right? So let's just have a brief think about what's going on there. Recall that the underlying picture is as follows. As the transducer vibrates up and down here, it generates a progressive wave which travels to the right. When this progressive wave reaches the fixed end over here, as we discussed earlier in the video, the progressive waves will be reflected and inverted back to the left. So they will look something like this. So these reflected waves will have the same wavelength and frequency as the incident waves moving to the right, and the same amplitude as well. Now, when these two, when the original waves moving to the right and the reflected waves meet, they will of course superpose, and at some point in time the two waves will be overlapping in the following way. So notice at this point here, or this position here, we've got a crest from the wave traveling to the right, and that's exactly in line with a trough from the wave traveling to the left. And since we're assuming that both of these waves have the same amplitude, we know that the displacements will be equal and opposite. So they will have the same magnitude but opposite sign. And we know from the principle of superposition that what that implies is that at this position here, the net effect, or the net or total displacement, will be 0. And that's exactly where a node will form. Okay? So at nodes, right, the waves, the underlying waves, are pi radians, or 180 degrees out of phase at all times, and so they superpose in such a way as to cause complete cancellation or zero displacement at all times. We'll discuss this in further detail in a follow-up video. Now, in contrast to nodes, all the particles that live or lie in between two consecutive nodes, so I'm referring to all these particles here in this loop, red, all these red ones and this green one here, you might recall from the simulation that all these particles are certainly not motionless. They're all vibrating or oscillating up and down. And in particular, these green particles that I've labeled with a capital AN, so this one here, here, and here, these are known as antinodes. The standard abbreviation is a capital AN. So wherever you have antinodes in a stationary wave, those points or positions will correspond to maximum displacement of the particles, and correspondingly antinodes correspond to points of maximum energy in a stationary wave. So let's just briefly talk about the formation of antinodes. Right? So recall, similar to what we were discussing about the formation of nodes, recall the underlying picture is that you've got a progressive wave moving to the right and a reflected progressive wave moving to the left. And at some point they might overlap right on top of each other. So here you can see I've drawn a little gap between the solid wave and the dashed wave here, but really that's just so that you can tell them apart. You should really think of these two waves as being right on top of each other. So what have we got? We've got here we've got two crests, right? And recall from superposition, that means that the net effect, the net displacement of those two crests superposing is going to give rise to, if you like, an even bigger crest. And that would explain this antinode here. Whereas, for example, here, we've got two troughs superposing. Okay, so that gives rise to an even bigger trough, or a trough with twice the amplitude of one of the troughs. Okay, so that might correspond to this antinode here. So basically antinodes are explained by the waves, the two underlying waves superposing in phase with each other, right? And again, we'll discuss this point in further detail in a follow-up video. Let me just momentarily go back to the simulation and point out something. So if I just press play here and pause it there, notice that the shape of the wave is a reflection along the equilibrium line of the initial shape of the wave. Okay, so from the time I pressed play to pause, the stationary wave has undergone half a cycle, or a time period, or half a time period, sorry. Alright, and I'm pointing this out because you ought to know that most of the time when we draw stationary waves, we draw in, or a reflection is drawn in like so, which shows what the stationary wave will look like half a cycle or half a time period equivalently later. So that's just worth knowing about. Another thing you ought to know about is some terminology. So I think I've already used the word loop earlier in this video. The word loop is used to just refer to a section of the stationary wave between one node and an adjacent node. So this whole region here that I've just boxed here, we would refer to this as a loop. So I'm sure I'll be using that as we go on in this video and in other videos. Now, this stationary wave that we've been looking at, it has a specific name. It's actually known as the third harmonic. And notice that it has 3 antinodes. Also, note that the third harmonic, its frequency here is 1.26 Hertz. So if I just go back to the simulation, what that means is that the third harmonic pattern emerges when the frequency of this transducer, the frequency at which it oscillates or vibrates up and down, is 1.26 Hertz. Now, there's nothing special about this value of frequency. when it comes to the third harmonic in general. It's just that for this particular system, so for this string or rope here and its particular properties such as its length, its mass, tension, etc., for this particular system, it turns out that the third harmonic will be present or will occur at a frequency of 1.26 Hertz. Let's see what happens now if we reduce the frequency down to 0.84 Hertz. Let me press play. Notice that we're seeing a new stationary wave pattern. So, what I'd like you to do now is to have a go at the following three questions. So the first one is, how many nodes and antinodes are there in this new stationary wave pattern that we're seeing? Second, what is the name of this stationary wave? And third, what is the shortest length of time for the stationary wave pattern to go from how it looks initially, so how it looks here in the picture, to looking completely horizontal, i.e. for all the particles to lie along the equilibrium line. So that's what I mean by this horizontal line here. Okay, so just to be clear, this initial configuration of the stationary wave pattern, we're assuming that all the particles in a loop, so for example this first loop here, we're assuming that all the particles are at maximum displacement, and the same is true for this second loop here. Alright, so please pause the video and have a go at these questions yourself, and when you're done, unpause it and we'll discuss the solutions. Okay, welcome back. Let's discuss question 1. Let me just draw the stationary wave pattern out here. So we've got these two loops. Let me draw in the reflection. And we know that this right end here, well, that's clamped, so that's going to be a node. And remember this end over at the left here, that's a node as well, effectively, even though the transducer does move up and down a little bit. We know that this point here, that's a point of maximum displacement, so that's going to be an antinode. And same goes for this point down here, that particle. And in between, we get a node. Alright, so so nodes and antinodes, they always alternate like this. Okay, so in other words, here we have 3 nodes, which I'll just abbreviate as capital N, and 2 antinodes. Let's look at question 2. What is the name of this stationary wave? Well, recall from the previous question that we determined that this stationary wave pattern has 2 antinodes. Now you might recall from earlier in the video when we were looking at the first stationary wave pattern that it had 3 antinodes and its name was the third harmonic. So here, because this stationary wave pattern has 2 antinodes, logically enough, the name of this stationary wave pattern is the second harmonic. Okay, so the number of antinodes determines which harmonic we're talking about. Let's move on to the third question. So hopefully you recall from earlier that for a stationary wave pattern, for it to go from its initial state, so for example that, to its reflected state, okay, this will take half a time period. Alright, so the time taken here will be the time period, whatever that is, divided by 2. And recall that the time period, capital T, is all about how long it takes for a particle to complete one whole cycle. So if a particle starts right at the top here, how long it will take for it to go right down to the bottom and then back up to the top where it started. That's one whole cycle traced out. Now, if we're interested in the stationary wave going from a configuration of maximum displacement to a configuration where the rope or the string looks completely horizontal, well, that's sort of just midway, halfway between it going from this to that, right? So the time taken for it to go from this state to here will be half of t over 2. So this will take a quarter of a time period. So that's what we need to work out here. And how do we do that? Well, notice up here, and I mentioned it as well, that the frequency of this stationary wave is 0.84 Hertz. Okay, and once you know that, you can work out the time period. The time period here is just given by 1 over the frequency. And what we're interested in specifically is a quarter of the time period. So t over 4 is just equal to 1 over 4f. And if I plug in, if I replace f now with 0.84, okay, it's 1 over 4 times 0.84. And if you plug that into your calculator and work it out, you will get 0.30 seconds to two significant figures, which is what we should be working to, because the frequency, the info given to us in the question is given to 2 significant figures. Let me just point out that the question asks for the shortest length of time, which suggests that if we wait longer than 0.30 seconds, we will see the stationary wave pattern look like this as well. And that makes sense, right? If we were to add on a time period onto 0.30 seconds, right, it will look exactly like this again, right? Because a time period, as I said earlier, is the time for one complete cycle. So one time period later, all the particles having moved up and down, well, other than the nodes, of course, will be back to where they are here. If we reduce the frequency of the transducer down to 0.42 Hertz, we see yet another stationary wave. Notice that in this stationary wave, there's just a single loop, and all the particles in this loop, other than the nodes, are moving in step or in phase with each other. So what we're looking at here is the first harmonic. And the first harmonic, as you might have expected by now, consists of just a single antinode and two nodes. And because you can't get any fewer than one antinode, this is the lowest frequency harmonic. Okay, so this is the lowest frequency at which a stationary wave will occur for this system. We've covered quite a bit of ground already in this video, so let's just take stock of where we are. So what we've seen is that when we get this vibration transducer to oscillate or vibrate at specific frequencies, these particular stationary wave patterns known as harmonics emerge. And each of these harmonics, for example the second harmonic, is characterized by a particular pattern of nodes, which are points of zero displacement, and antinodes, which are points of maximum displacement. So the second harmonic, as you can see, has 3 nodes and 2 antinodes. Now, if you look at the frequencies at which these harmonics occur, you might spot a pattern. Notice that the second harmonic is simply 2 times the first harmonic, the frequency of the first harmonic. And similarly, the third harmonic is simply 3 times the frequency of the first harmonic. So for this reason, the first harmonic is often known as the fundamental, which makes sense because its frequency determines the frequencies of all the other harmonics. So let's try to get a better understanding of the pattern that we're seeing here. Let's call the distance from the node at the transducer to the node at the clamp, let's call that distance L. If you look at the first harmonic here, you can see that we can fit one loop, or equivalently one whole or one half wavelength, into this distance, right? If you look at the second harmonic, notice that we can fit two loops, or equivalently two half wavelengths, into the distance L. And of course in the third harmonic you can see we can fit three loops or three half wavelengths into the same distance L. So because the ends of the string are fixed, i.e. they have to be nodes, this places a constraint on the number of loops or the number of half wavelengths that we can fit in to this distance L, right? We're allowed to fit in 1, 2 or 3 loops, or 15 loops, or 79 loops, right? We can fit in a whole number of loops or half wavelengths, but we're not allowed to fit in 1.5 loops or 2.75 loops. You can try this out for yourself to convince yourself that it's not possible. So let's consider all of this a bit more generally. Let's consider the nth harmonic at a frequency f subscript n. Now, as you know, the nth harmonic will have 1, 2, 3, up to n antinodes, okay? And that means n loops or n half wavelengths should fit into the distance L from the left end to the right end. So I'm saying a half wavelength here is lambda n, so lambda subscript n divided by 2. And n of these half wavelengths have got to fit in to this distance L. So let's have a look at the implications of this if we examine the maths. So we're saying n of these half wavelengths must equal L, right? So let's rearrange for lambda n. Lambda n is equal to 2L divided by n. Now, we know that there's a relationship between wavelength and frequency, right? That's just the wave equation. Okay, so remember the wave equation tells us that the frequency fn and wavelength lambda n, if you multiply them together, it should give you the wave speed, right? The speed of the waves of these transverse waves on this string. So if we combine these two things together, or rather, let me here just first make fn the subject. It's v divided by lambda n. Now if we combine this with what we've got written over here, okay, we can put these two things together and we find that Vfn, the frequency of the nth harmonic, is equal to n times v, the wave speed, over 2L. Now, to see the implications of this just a bit more clearly, if we just set n equal to 1, so in other words, if we just consider the first harmonic, right, then using what we've just found here, this relationship here, that would mean that f1, the frequency of the first harmonic, would equal n. Well, n is just 1, so 1 times v over 2l. And so we can write this relationship here equivalently as Fn, the frequency of the nth harmonic, is n times the frequency of the first harmonic. And we're done with our little derivation here. So this provides theoretical justification for the things that we saw in our simulation. So to remind you, we found here that the frequency of the second harmonic, right, so if n is equal to 2, is simply 2 times the frequency of the first harmonic, which happened to be 0.42 Hertz here. And the frequency of the third harmonic, so if we set n equal to 3, is equal to 3 times the frequency of the first harmonic. Okay, so we've really just proved or provided theoretical justification for that pattern. Just remember that n here stands for a positive whole number or integer. As I said earlier, you can't fit anything other than an integer number of loops into this distance here. So n can't be, for example, 1.5 or 2.75. Let me just point out that if you're studying AQA or edXL, you need to be aware of the following. So for the situation or scenario we've been looking at of stationary waves on a string, you need to be aware that the speed of transverse waves on a string is given by the square root of the tension of the string divided by the mass per unit length of the string, mu here. Okay, so the formula or formulae we derived can be equivalently expressed as I've written here in this box over here. So be aware that this replacing v with square root of t over mu, this is only if we're talking about transverse waves on a string. Alright, if we were talking about stationary waves in another setting, and there are many settings, such as you can get stationary waves with microwaves, okay, so a type of electromagnetic wave, or sound waves even, this replacement would not make sense, because then for those waves the wave speed is not given by this formula here. You don't need to know this formula if you're studying OCR, but having said that, I do recall questions where they will give you this formula or something related to it, and you'll have to work with it. If you're studying something other than AQA, edXL, or OCR, I recommend you check the specification to see whether you need to know this. We've covered quite a lot of ground in this video, so let's summarize the key points. At the beginning of the video, we examined what happens when progressive waves travel towards a fixed end. So this dot here represents a fixed end which cannot move. And we found that the waves, they reflect back in the opposite direction. So these waves here move back to the left after reflecting. And importantly, what we found was that the reflected waves, they have the same amplitude, wavelength, and frequency as the incoming or incident waves. And this is a key ingredient when it comes to the formation of stationary waves. If this weren't true, so for example, if the reflected waves didn't have the same amplitude as the incoming waves, then stationary waves would not form. Now recall that if we have a vibration transducer, which is just like a rod that oscillates up and down, then that sends out or generates progressive waves continuously, which move to the right and then get reflected. So in that case, what we would see is that these incident or incoming waves would superpose with the reflected waves. Now you might recall that in general, at any old frequency, nothing interesting happens. Okay, it's only at specific frequencies that we see stationary wave patterns. So for example, here I've sketched out what's known as the third harmonic, which would happen at a specific frequency, which I'm calling f free or subscript free here. Recall that a stationary wave is characterized by positions or points of nodes, which are points of zero displacement of the particle at these points at all times, and points known as antinodes, where the particles oscillate with maximum amplitude. Recall that we discussed that the frequencies of possible stationary waves or harmonics are always given by a whole number or integer multiple of the frequency of the first harmonic. So we can say that the frequency of the nth harmonic, Fn, is determined by the frequency of the first harmonic, F1. And that's summarized by just this very simple formula here, that Fn, the frequency of the nth harmonic, is n times the frequency of the first harmonic, F1, where F1 is given by the wave speed divided by 2 times L, where L is the length of the string, so the distance from the fixed end at the left to the fixed end or node at the right. While in this video we discussed exclusively transverse stationary waves on a string, it's really important to note that stationary waves aren't just a phenomena which can take place on strings. Okay, we can also generate stationary waves from microwaves or sound waves, all sorts of other types and classes of waves. Let me finish by saying thanks to PhET for their terrific simulation that I've made use of in this video. I'll leave a link to that simulation in the description, and as usual I highly recommend you check it out to have a play around with it and develop your own understanding and intuition. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment if you have any thoughts or suggestions. Thank you for listening, and hope to see you soon.